Welcome back to AI.Code.Cast, where we tackle those fun coding challenges. Today, we're going to be looking at how to create a deep copy of a linked list. But there's a twist.
That's right, yeah. We're not talking about your everyday average linked list. It gets a little bit more complex when we start talking about random pointers.
Okay, so for our listeners who may not be familiar, imagine like a chain of boxes. Each box has some data in it and then a pointer to the next box. But here's the fun part. Each box also has a random pointer, which can point to any other box in that chain.
Yeah, and the challenge here is that we want to create an exact replica of this entire structure, a deep copy. And
Yeah.
so not just copying the data that's in each box, but actually recreating the entire web of connections that are formed by these random pointers.
Okay, so if we were just kind of like think about this from the top, brute force, how would we tackle this?
Well, I mean, the first thing that comes to mind is, right, we can make a copy of every single box and link them up in the same order as the original list. Then we go back to our original list, and for each new box, we go and find the box that that random pointer is supposed to be connected to, and then we go and find the corresponding copy in the new list that we made.
Yeah, that makes sense to me, just meticulously going through and copying each connection. But something tells me that's not going to be the most efficient way, especially if we have a really long list.
Yeah, you're absolutely right. I mean, if our linked list has thousands or even millions of these boxes, this brute force method is going to involve a lot of searching and comparing, and it's going to be very, very slow, very computationally expensive. So we need a smarter approach.
Yeah, okay, so how do we do this in a smarter way? I'm thinking like we need some way to just quickly find the right connections without having to go search through the entire list every time. What if we used something like a lookup table?
You're on the right track, and actually encoding that data structure that we use for that is called a hash map.
A hash map. Okay, so how would we use a hash map to help us solve this?
Yeah, so think of a hash map like a dictionary, where each word, or in our case, each box in the original list, has a corresponding definition, which would be the corresponding copy of that box in the new list.
Okay, so as we're creating a copy of each box for the original list, we're also adding an entry into our hash map that essentially says this original box maps to this new copy box.
Yeah, exactly. And what's great about the hash map is that it lets us find those mappings almost instantly. So when we need to set the random pointer for a new box, we can just quickly look up in our hash map and find the corresponding copy and just set the pointer and be done with it. No more searching through the entire list.
Gotcha. I like this hash map approach. I think it's going to be a lot more efficient than that brute force idea we talked about at the beginning. Can you walk me through, maybe with an example, how this would actually work, step by step?
Absolutely. Let's take a simple linked list with just 3 boxes. We can call them A, B, and C. Box A's random pointer points to box C. Box B's random pointer points to A. And box C's random pointer is null, meaning it's not pointing to anything.
Okay, so first we'd create copies of those boxes. So A prime, B prime, and C prime.
Right. And as we create each copy, we're going to add that mapping to our hash map. So A to A prime, B to B prime, and C to C prime. Now we're ready to actually start setting those random pointers.
Okay, so for A prime, we know that its random pointer needs to point to the copy of C, which is C prime. So that's where the hash map comes into play.
That's exactly right. We look up C in our hash map, and it'll immediately tell us, hey, the copy of C is C prime. So we'll just set A prime's random pointer to C prime, and we've recreated that connection.
And then we do this same process for each box in the list using the hash map to quickly find the connections.
That's right. For B prime, we look up A in our hash map and see that it maps to A prime, and we set B prime's random pointer to A prime. Since C's random pointer is null, C prime's random pointer will also be null.
Awesome. This makes a lot of sense. I think I'm understanding how the hash map helps us to create this deep copy of a linked list. But I'm curious, what about like the efficiency of this in terms of time and space complexity?
That's a great question. And we'll dive into that analysis of this hash map solution right after
Use
we
us
get
back. So we're back. Yeah. And I'm really interested to kind of dive into the efficiency of this hash map approach. What is the time and space complexity?
Yeah, so when we talk about efficiency of an algorithm, we often look at time and space complexity. Time complexity basically refers to how does the time it takes to run this algorithm grow as the size of our input, which in this case is our linked list, as that grows. How does that time grow?
Okay, so for our hash map solution,
Yeah.
how would we analyze that time complexity?
So basically, we're doing 2 passes through our linked list. The first one is we create a new copy of each of those nodes and store the mappings in a hash map. And then we iterate through again to set the next and random pointers using that hash map. So both of those iterations are going to take time proportional to the number of nodes in the list.
Okay, so if we had n nodes in the list, we're basically doing n operations in each of those iterations.
Yeah.
So is that what we call linear time complexity?
Exactly. Yeah. So it's O of n. The time it takes to actually execute this algorithm grows linearly with the size of the linked list.
Gotcha, that makes sense. And then what about space complexity?
Yeah, so space complexity basically refers to how much extra memory are we using in our algorithm. And in this case, the main thing that's contributing to that is our hash map.
So as the linked list grows, the hash map also has to grow to accommodate all of those mappings. So that would also be a linear space complexity as well.
Yeah, you're absolutely right. The space complexity of this hash map solution is also O of n because, at worst, our hash map needs to store a mapping for every single node in that original list.
Okay, so we've got a solution that's pretty clear. The time complexity is pretty good at O of n, but the trade-off is we are using extra memory with that hash map. So I'm curious, is there a way to maybe do this using even less memory, maybe even constant space?
So there is actually a really clever way to solve this problem using only a constant amount of extra space, and it's called the interweaving nodes method.
Interweaving nodes. Okay, I like the sound of that. Tell me more.
Yeah, so instead of creating a separate hash map, we're actually going to be clever and utilize the existing structure of our list. So imagine you're kind of weaving a tapestry, right? Instead of creating a separate thread for the copy, you're meticulously weaving it between the existing one.
So we're essentially creating a copy node for each original node
Yeah.
and then inserting it right after the original one in the list. So it's like we have the zipper pattern with the original and the copied nodes kind of like interlocked.
You got it. Yeah, so if you had like A, B, C, that was your original. It's going to become A prime, B prime, C prime. So A prime, B prime, C prime are the new copies that we've created.
Okay, and so I see how that helps us because now if we're at node A and we know its random pointer points to C, we know that the copy of C, C prime is right after C in our interwoven list.
Exactly, yeah. So to set the random pointer for A prime, we can just go A.random.next. So we follow A's random pointer to C, and then we just take one more hop over, and now we're at C prime.
Wow. So no need for the hash map. We've got the information right there in the structure, and then we can repeat that same process for each of the copied nodes using that structure.
Yeah.
But now how do we separate this interwoven list
Yeah.
back into the original and the copy?
Yeah, so it's basically like we're unzipping that zipper that we created. We're going to go through and we're going to adjust the next pointer. So for each original node, we're going to set its next pointer back to the original next node, skipping over the copy. And then for each copied node, we're going to set its next pointer to the copy of the next node.
Okay, so at the end of this pointer manipulation, we end up with our original list back in its original form, and then a completely separate, correctly linked copy. And we did all that without needing to use that extra memory overhead of a hash map.
Exactly, yeah. So the interweaving nodes method is really clever in that it just manipulates the structure of the list to be able to get that constant space complexity.
Wow, okay. I have to admit, this interweaving nodes is a little mind-bendy for me. I think I'm going to need a step-by-step walkthrough with an example to really solidify this in my mind.
You got it. Let's go through a concrete example so you can see all this magic happening.
All right, let's dive into that example. Let's use the same simple linked list we've been working with, nodes A, B, and C, where A's random pointer is to C, B's to A, and C's is null.
Okay, so we start with our list, A, B, C. And the first thing we do is weave in those copied nodes, create that zipper you talked about.
All right, so we'd put A prime right after A, then B prime after B, and C prime after C. So it looks like A, B, 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 C. And I can really see now how that kind of implicitly stores the mapping, like right after the original is the copy.
Exactly. Now we need to deal with those random pointers. So let's start with A. It's pointing to C. How do we set A prime's random pointer?
Well, we know that the copy of C, C prime, is going to be right after C in our interwoven list.
Right. So to set A prime's random pointer, we just use A.random.next. We follow A's random pointer, which takes us to C, and then take one more hop, and now we're at C prime.
So A prime dot random is now pointing at C prime.
Perfect. What about B prime?
Same idea. We follow B's random pointer, which would lead us to A, and then one more hop and we land at A prime. So B prime dot random would point to A prime.
And C's random pointer is null, so C primes would be null as well. Got it. So now we've got all the random pointers set correctly, but we still have that interwoven list. Time for the unzipping. Exactly. So for unzipping, we adjust those next pointers. Starting with A, we want it to point to B, skipping over A prime. So it's back to the original A, B.
And then for A prime, we want it to point to B prime, skipping over B. So A prime, EB prime. And then we just keep following that pattern down the list.
Yeah, B, E, and
Yeah.
then B prime, E, C prime, and C prime's next pointer stays null.
So we've got our original list back in its original form, A, B, C, and a completely separate, properly linked copy, A, B, C. And we did it without needing that extra memory from a hash map. Incredible.
It's pretty neat. The interweaving nodes method is a great example of how we can be clever with our data structures to get some really efficient results.
Totally. So we've looked at a couple different ways to solve this deep copy problem. The brute force way, the hash map, and this really cool interweaving nodes method. It's really amazing to see how much depth there is to even a seemingly simple problem like copying a linked list.
It definitely shows you how much thought and creativity goes into designing efficient algorithms. It's not just about brute forcing your way through, it's about finding elegant solutions that leverage the structure of the data itself.
Absolutely. Well, I don't know about you, but I am feeling inspired. Thanks for joining on this deep dive.
It was my pleasure.
And to all our listeners out there, remember to keep that curiosity going, keep experimenting, and we'll see you next time on AI.Code.Cast.